Somebody starting recording? Okay.
Yeah.
Okay. So welcome to this next session of HALG. We will have two talks now. Before we start, let me remind all of you that you should all stay muted during the talks and ask the questions through the chat box on the right of your screen. I will then read the questions aloud to the speaker. During this session, we'll have two talks. The first talk will be about log-approximate-rank conjecture and essential recent breakthroughs around in this area, and it will be given by Arkadev Chattopadhyay from Tata Institute for Fundamental Research in Mumbai. So, yeah, I think we can start. Arkadev.
Oh, thank you, Michal.
Yeah.
I must apologize that I couldn't get my video working, so sorry for remaining invisible. But thanks a lot for the organizers for inviting me to this great workshop. Okay, so this is a joint work with my former student Nikhil Mande, who's now at Georgetown, and with my current student Suhail Sharif. Okay, oh, somehow this is not working. I cannot go to the next page for some reason. Okay, let's see.
Maybe you should yeah, put a presentation mode.
Well,
maybe page down. Maybe click on page down, page up.
Yeah, okay, that's right. Okay, page down works. Thanks. Okay, so let's look at the very familiar model of two-party communication that was introduced more than 40 years ago now by Andy Yao. So I'm sure you're all familiar with this model, but nevertheless, let me quickly remind you. So there are two all-powerful players, Alice and Bob, and they want to evaluate some function. And the problem is Alice gets only one set of the input bits, which we call X. Bob gets the remaining one, which we call Y. And they decide on some protocol beforehand, according to which they communicate with each other. Their objective is to be able to evaluate the function on all possible inputs that they may get with the least amount of communication between them. And the protocol proceeds in rounds. Alice first communicates some bit to Bob, and then Bob answers back. And what Alice communicates only depends on what she sees, and what Bob communicates back is what he receives from Alice and what he sees on his side. And this goes on forever, for some time. And then on the rth round, the answer is given out. So this is the well-known model. And the question that one is interested is, in the worst case, how many bits do Alice and Bob need to communicate with each other? This is called the deterministic communication complexity of F, which we will denote as D of F. And it's quite simple to see that this is at most n plus 1, because Alice could just communicate everything. The question is, what kind of structure, combinatorial, algebraic, or otherwise, if that structure is possessed by F, how can we then use that to save on the communication between Alice and Bob? And it's simple to see that there are some easy functions, like, for example, if Alice and Bob were wishing to communicate the parity, then, of the number of ones that they see on their inputs, then you can just do it in 2 bits. And similarly for symmetric functions, so this is well known. So this was defined, as I said, 40 years ago, and it has come up with unexpected connections. I think it has surpassed possibly the wildest dreams of Andy Yao. So new connections keep emerging, and the list keeps going on. Here I just give you some examples. There are some obvious ones like distributed computing, streaming algorithms, but then there are sort of non-obvious things also, like extension complexity, a recently very active area where communication complexity has played a very decisive role in solving problems. Okay, so the field has matured enough. There are some classical books, there are new books. The one by Anup Rao and Amir Yehudayov is, as far as I know, the most recent book, and I urge you to look into it. It's a really very nicely written book. And it shows you that this field has a very rich mathematical theory. And the field is driven now, we can say, equally by applications that seem to be all the while coming up, and also some basic questions that are inherent to this model. Okay, and we're going to talk about one such basic question. In fact, one of the most basic questions, the first question that one might think of in some sense about the model. So what is this quantity D of F, deterministic communication complexity of F? Is it combinatorial? Is it information theoretic? Because after all, Alice and Bob want to reduce the amount of information exchange. These two seem very natural flavor for the quantity in question. Or is it algebraic? Now, of course, it's not clear what has algebra got to do with this question, but it's now well known that there is a very simple way to view the problem via a matrix called the communication matrix that affords tools from linear algebra to be brought in. A very simple idea. The rows of this matrix are indexed by the set of possible inputs that Alice may have, the columns by what Bob may have. It's a Boolean matrix, so at the x, y entry of this matrix, you just put the value of the function f. And this matrix we will call M of f, M subset of f. Okay? And this fact, there's a very nice, simple, powerful fact, first observed by, I think, Melhorn and Schmidt, that the rank of this matrix is at most 2 to the deterministic communication complexity of f. Now this rank, this relationship is actually true over any field. I haven't specified the field, but in this talk, for the purpose of this talk, my field would be set with characteristics of the real field. We're only going to talk about real fields. Okay, but the fact is true for all fields. And this is a very useful tool to prove lower bounds on the communication complexity of f by the log of the rank. Okay? So let me remind you quickly why this simple fact is true. The protocols can be viewed in many ways. One of the most convenient ways to view it as a protocol tree, where Alice and Bob alternate communicating. So this protocol tree has some nodes possessed by Alice, some by Bob, and let's keep it layered. So what happens is, given an input x and y, it's accepted if in the protocol tree, the path that you trace out reaches a leaf labeled by 1. Okay, that's a very natural way to view the computation. And you can ask this question about, what are the set of inputs that reach a particular leaf? And this turns out to have a very nice structure, what is called a combinatorial rectangle. So basically you need to find out all the inputs that Alice gets where she answers red, and all the inputs that Bob gets where he answers blue. The product set, the product of these two sets, the Cartesian product of these two sets, is exactly the set of inputs which will hit the leaf L. And this has immediate rank implications because you can build sort of the truth table of the function. You look at the set of all inputs that reach leaf L, and this is a combinatorial rectangle. In other words, it's a rank 1 matrix because the product of two vectors. And now you look at the set of all inputs that reach either leaf L1 or L2, and by the union bound, this is again at most rank 2. And there can be at most 2 to the C leaves because the height of the decision tree, the protocol tree was at most C. So, just a union bound shows that the inputs that reach leaf 1, I mean, the rank of this matrix is at most 2 to the C. And this gives us the desired fact that was first observed by Melhorn and Schmidt. And this shows that deterministic communication complexity is lower bounded by the log of the rank of the corresponding matrix. Okay. Now, whenever you have such a bound, a natural question is this tight or is it loose? It's good that you have this very nice characterization, but does it actually characterize the matrix? So that's a question that we'll come back to. But before that, we go there. Let me just show you one example, which will be actually very important in what I have to say to see this this connection in action, which is for the equality function. So this is the first function that one learns when one is taking a course in communication complexity. Alice and Bob wish to determine if the two strings as strings are equal, exactly identical. And if you look at the communication matrix of this function, then you get the identity matrix, right? On the diagonal, you have ones, rest you have 0. And this matrix has a very simple fact, has full rank, 2 to the n, and immediately you get the consequence that the deterministic communication complexity of equality is as high as it can. Okay. So the question now is, so it's very nice, so it can give you very strong lower bounds which are tight, but is it always tight? And the question, and the basic question is like, is rank somehow characterizing the communication complexity of function, the log of the rank? Okay. If it did, then this would reduce the study of communication complexity to essentially, linear algebra. Okay. And this was, in the spirit, this conjecture due to Lovash and Sachs was posed more than 30 years ago, when they asserted that there is some universal constant alpha, such that the deterministic communication complexity of every function f is upper bounded by the log raised to the power, the log of the rank raised to the power alpha. Okay, and this has come to be known in the field as the log rank conjecture. It's a notorious conjecture. It's wide open, despite its simplicity and very basic nature. And one reason this conjecture seems to be very hard to sort of get your hands on is it's very hard, very difficult to come up with interesting low rank Boolean matrices. The only way that I know of constructing low rank matrices is to come up with a function that has low communication complexity. And because it has low communication complexity, it has low rank. But that's never going to give you a counterexample, if there were one, for the log rank conjecture. Okay, so it's very hard to come up with low rank interesting things. So what have we got as facts supporting this conjecture? Very little. Up until 2013, we didn't even know any non-trivial upper bound on the deterministic communication complexity of a function using rank. And then Shahar Lovett had this breakthrough where he was able to show that it's upper bounded by root of the rank up to polylog factors and ignoring polylog. So that's the best result that we have going for the conjecture. That's what I mean by for. And the worst thing against this conjecture is also rather weak and had to wait all the way until 2015, where Gus, Pitassi, and Watson in another breakthrough showed that this alpha, the universal constant posited by Lovash and Sachs, has to be at least 2. Okay, so that's all we know about this conjecture. So of course, I have no progress to report on this tantalizing conjecture. I will at this point shift gears and look at what would sound more ambitious, basically randomized communication complexity. So again, we can ask, for randomized communication complexity, is there a rank or rank-like measure that can, in spirit, be characterizing randomized communication complexity of Boolean functions? Well, turns out that rank by itself is not enough, and this is witnessed by, again, the equality function as I was referring to. It has very large communication complexity, n+1, very large rank we saw, but it turns out that this is a very simple, beautiful protocols, efficient protocols in the randomized world. There are many. I just give you one example, quick one. So Alice just samples privately, a prime from the first n square primes. She views, both Alice and Bob view their inputs as n-bit numbers, and then all Alice does is sends to Bob. Sorry, I forgot to mention here. She sends both x mod p, which is about worth log n bits, and also the prime that she sampled to Bob. And then all that Bob does is to check if x and y are congruent modulo p. If they are, he answers yes. If they aren't, he answers no. So that's a very natural protocol. And again, it's very simple to check that, if x and y are indeed different, then with high probability they will catch it. In particular, the way I showed you, the probability of making an error here is very small, like 1 over n. It's linearly small. Okay. And the communication complexity, there's a typo here. It should be 3 log n plus log of n. Doesn't matter, but it's very small. Okay. So this shows that, equality already shows you that just log of the rank is not a good measure to hope to characterize the randomized communication complexity. But as I said, it's too much to hope that rank itself would be able to capture randomized communication complexity. More generally, what we'd like to know is there some rank-like measure that does. Okay, and it'll turn out that there is, and for that, let me quickly remind you, again, go back to the protocol tree. So now we look at the randomized protocol tree. Additionally, now Alice and Bob have got private random strings on their side. So the protocol tree acts on two things. One are the inputs of Alice and Bob, and also on the private random coins. Okay, and what we will now be interested is, given an input xy, what's the probability that it's going to be accepted by a given protocol? And that's the same as the protocol reaching a particular one leaf. So we want to find out the probability it reaches one leaf, a particular leaf labeled 1. So let's look at such a leaf L. As before, now it can be written in some sort of a product like fashion, because what we are interested in understanding is what's the probability that on the input x Alice answers according to this the red answers, yeah, and what's the probability that Bob answers blue on y, and these are again independent, right? So so it's the product. The probability of reaching this leaf L is exactly the product of these two probabilities, and this again affords a very nice picture. What we're now going to look at is not the communication matrix, but the acceptance probability matrix of a protocol. Okay, so the xyth entry of this matrix is going to tell you what's the probability the protocol pi, a given protocol pi, is going to accept the input xy. Okay, and let's now first try to understand what's the probability that xy reaches a particular leaf L, and from what we saw, this can be written as the outer product of two vectors. Okay, and this just means that this probability matrix of reaching L is a rank 1 matrix. And what you're going to do is to get the acceptance probability matrix finally is to sum up the probabilities over all leaves L, which are 1 label leaves. Okay, and there are again at most 2 to the c leaves. So what all in all this shows you, the first observation is that if I have a communication protocol pi, then the acceptance probability matrix of that protocol has rank at most 2 to the cost pi. Okay, and the second observation is that the first one is true for any protocol pi. The second observation is, if pi was actually computing f with error at most epsilon, then we know that this acceptance probability matrix approximates the communication matrix pointwise within epsilon. Okay, if the communication matrix had at a point 1, this acceptance probability should be at least 1 minus epsilon. If it had just 0, the the acceptance probability matrix would be at most epsilon. Okay, so it pointwise approximates within epsilon. So therefore, this shows you that even though the communication matrix may have high rank, if it had a small randomized protocol, it can be pointwise approximated well within epsilon by a low rank matrix. Okay, and this is the notion of approximate rank, epsilon approximate rank. Okay, your epsilon approximate rank is small if you can pointwise approximate a function within epsilon, the matrix within epsilon, by a low rank matrix. And from what we discussed, it follows that the epsilon approximate rank of my communication matrix is at most 2 to the randomized communication complexity of f. So this again gives me a way of lower bounding the randomized communication complexity. So the question again is, how tight is this? Okay, turns out that most known methods until our work was basically, lower bounding some complexity measure which was dominated by the approximate rank. So in every case when we were able to prove a strong lower bound on the randomized communication matrix, it was basically because its approximate rank was large. And this gave Philip to the idea that this is somehow tight. And if you search the Wikipedia, this is an article from its 2005 that appeared. which said the following thing, that for a randomized protocol, the number of bits exchanged in the worst case is conjectured to be polynomially related to the following absurd formula. Okay. And what's there in the absurd formula is exactly the approximate rank of the communication matrix characterizing the randomized communication complexity. And turns out the author of this article is called Forsgård. So we attribute this conjecture to, it first made, Forsgård happened to be a student at the University of Michigan at Ann Arbor, where somebody was teaching a course where informally this conjecture was first made. And then later Lee and Schreibman in their monograph on communication complexity christened it with the name of the log-approximate-rank conjecture. So just like the log-rank conjecture, it asserts the existence of a universal constant beta, says that the randomized communication complexity is always upper bounded by the log of the approximate rank raised to the power beta. Okay, so one interesting thing is, which is not obvious, you have to carefully argue, is that it's actually a strict strengthening of the log-rank conjecture. Interestingly, it implies the log-rank conjecture. This was shown by Gavinsky and Lovett in 2013. And as I said, you know, every lower bound that we have is indirectly proven using a lower bound on the log approximate rank. So the question is now how likely one would think is that log approximate rank should be true. It depended on whom you talk to, but in any case, the best lower bounds that we had, or things going against the log approximate rank conjecture before our work, was the set of following two results. So the classical result is on set disjointness, which is a very well-known function. The lower bound on set disjointness and the quantum upper bound proven by Burman, Cleve, and Wigderson basically implies that this constant beta has to be at least 2. Okay? This was for a while the best lower bound that we had on beta, and then again very recently Gus Pitassi and Watson were able to show that beta needs to be at least 4 by constructing a more concocted function. Okay.
There is a question on the board. Is there an easy way to see for the MP for equality? I don't really understood the question.
What is MP? So I don't know what is.
So MP, I think it was a few slides ago. The acceptance probability.
The matrix M.
Yeah.
I mean, I showed you. So maybe there are. Maybe he means the question means without using a communication protocol. I'll take that offline.
Okay.
Yeah. Let me continue with it. Okay.
Also, there was a question about the conjecture. Did Forsgård the conjecture polynomially related or polylogarithmically related?
It was polylogarithmically.
I guess so. Yeah.
Yeah.
Good. Right.
Okay. Yeah. Okay. So so you know why one should be interested in the log approximate rank conjecture. Well, of course, it's a very interesting conjecture. It's about the nature of communication. So just like the log rank conjecture is fundamental, one needs to know. But more interestingly, the log approximate rank conjecture over time acquired some sort of a mythic proposal. It started becoming too powerful. It implied all the things that you sort of wanted to prove in communication complexity. I will give you just highlight 2 examples here. Very active areas. One is the relationship of quantum protocols versus classical protocols. It's an outstanding problem to determine what is the nature. Does quantum protocol afford super polynomial advantage over classical randomized protocols for total functions? This is still open. The log approximate rank conjecture, if it implied this. So if you are somebody who does not believe in the equality of these 2 classes, then you needed to disprove the log approximate rank conjecture. It came in your way. Another interesting thing that the log approximate rank conjecture implied is this thing at the bottom, which is communication versus information, another very interesting area, which basically the conjecture asserts that communication complexity is equal to the information complexity. Although the goals of the two things are very different, but it ultimately is, polynomially related. The log approximate rank conjecture again implied that. Okay, it implied a host of other things, probably too much, and what we are able to show in this work, the main theorem, is that there's actually a very simple function, very natural, very simple function that gives a very strong refutation of the log approximate rank conjecture. Our function has rank, approximate rank, order n square, where n is the number of beats that each player holds, and the randomized communication complexity is square root of n. So this gives us an exponential separation of the log approximate rank and the randomized communication complexity. So in the few minutes that I have, let me show you the function. So the function is very simple. So I'll construct in two stages. The first stage will be what I call the sinc function. So this comes from insight into query complexity. So my function will be defined on the edges of a complete graph on m vertices. Okay, and so these edges are my variables, and assignment, Boolean assignment to these variables is going to orient the edges. So let's say if I assign 0 to a particular edge, then it gets oriented from the higher numbered vertex to the lower numbered vertex. Vertices are somehow enumerated in some arbitrary way. Okay, and so every assignment orients the graph, and now all you want to determine is if this particular graph has a sinc or not. That's all. That's what the function wants to determine. Now this function has, although it's very simple, it has a remarkable property. It is almost like a promised function, although it's a total function. All inputs are valid inputs. The promise is that if there is a sinc, there's at most one sinc. Okay, and this is a very, very important aspect of this function, which we are going to soon use. So now let me create a communication function out of this function, which is going to be just the lift of this function with XOR. So now Alice and Bob get two inputs, X and Y, and they bitwise XOR the inputs to get n-bit input string Z, and all you need to check is whether this Z has a sinc or not. Z is the assignment to my sinc function. So that's all. That's our F. Okay, sinc of XOR. X is with Alice, Y is with Bob, and this is the function. This simple function refutes the log approximate rank conjecture. So let me quickly tell you why the approximate rank is low. This is a very simple proof where we're going to crucially use the promise, a sort of promise that if there is a sinc, there's at most one. Okay, so how does the proof go? So notice that all I need to do is to check whether I need to check vertex by vertex whether vertex 1 is a sinc or vertex 2 is a sinc, and so on. So if I need to check whether vertex vi is a string, I need to see if the edges incident to that vertices have a particular assignment. So I've shown you here the required assignments, and so I can rewrite the sinc of XOR as a sum of equalities. So I'm going to check to check if the ith vertex is a sinc, I need to check whether the bitwise XOR of X and Y projected down to VI, the XOR is equal to the string AI that I'm looking for. Okay, that will verify if if vertex I is a string. And why can I do a sum? I can do a sum precisely because if there's a sinc, there's exactly one sinc. Okay, and that's the crucial property. And you just massage it, and it boils down to checking equality of two strings, XVI and Y prime VI. And now we can appeal to what I just showed you, the first thing that, equality has a small approximate rank because there's a simple protocol, randomized protocol. And I'm going to check m equalities, each has m to the 4 rank. So by a union bound, this shows me that the rank is m to the 5. And actually it shows me more, even the non-negative rank, because this rank was derived from protocols, the non-negative rank is also very small. Okay, so I didn't deliver my promise. I showed you that I claimed that I will be able to show n square, but because I'm here using non-negative rank, with a bit more care, I can show you that it's order n square. So I think I'm running out of time, right?
Indeed,
Okay.
you are, but
Okay,
but this is very interesting. Yeah.
Okay, so maybe I'll skip the lower bound slides because it requires careful work. It's technical, but it follows Yao's principle. So let me quickly go back, go to some open problems here. So the summary and the many open problems that emerge from this work are the following. So first of all, it's sort of interesting to understand what other counterexamples can we have. Is the function that we showed a singularity? In the sense, like, you have to formally define it, and we can formally define it in some way, okay? I mean, are functions of this kind only known counterexamples to the log approximate rank? So this, I think, is a very interesting question. And what we showed here is, to sum up, is that, you know, the randomized complexity of sinc of XOR is root n, the rank, approximate rank, is order n square. So you see there's a fourth power separation between the two. Mm-hmm. Is this the best possible separation? Can you narrow down the separation, right? Can you show the approximate rank and randomized complexity are even closer than this? And indeed, as I showed you, in the case of deterministic complexity, we know that deterministic complexity is always bounded by the root of the rank. This was the breakthrough work of Shahar-Lovett. In a recent work, Gal and Syed showed that if you use quantum communication protocols, then indeed square root of the approximate rank, so just please read that as square root of the approximate rank and not rank, is an upper bound on the quantum communication complexity. So where does randomized lie? This is still not known. We have a fourth power separation. Could we push it to a quadratic separation? This is an interesting question, and it's connected to getting other counterexamples. Finally, how does the function landscape look like? Total function, you know, right after our work, a set of two authors independently were able to show that even the quantum log rank conjecture is false, and the same function refutes the quantum log rank conjecture, even for XOR functions. So all these conjectures that were implied by log approximate rank conjecture, they still are open, and even to show, make progress on them for the very special case of XOR functions is very interesting. I had a few more open questions, but I think I'm taking too much time.
I think we need to slowly go. Yeah.
Okay, so I just finished it.
Yeah, so thank you very much for the very nice talk. I don't think that we have a protocol for clapping here, but you can express your interest in the talk in the comments. We probably have 1 or 2 minutes for 1 or 2 very quick questions. So if you have any question, please put them into the chat box now.
So I think somebody, was it Yossi who raised his hand?
Yossi?
We're just clapping.
Ah, it was a clapping her hand, yeah.
The clapping, yeah.
Yeah, indeed. Yeah, seems everything was clear. So I think that for the sake of not wasting more time, let's thank Arkadev again, and we proceed to the next talk.